Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we discuss a new concept regarding the force exerted by a jet of water on a series of radial curve vents. In our previous lecture, we have seen the force exerted by a jet of water on a series of flat vents. Okay, series of flat vents. Now it is slightly different. This is radial curved vents. So you can see a wheel is there, and in the wheel number of vents are present. So this diagram I have taken from the book. So let's consider a series of radial curve vents which is mounted on a wheel, and this is one wheel, this is one these are the vanes, not wheel. So these are the radial curve vanes. This is vane, this is also vane, this is also vane. Vane number 1, vane number 2, vane number 3, you can say. So number of vanes are present. Even more number of vanes also can be mounted on this. Only few part we have shown here, and this part is, this is actually wheel. So if you want to see the exact position of this one, we can draw another one wheel. Like this is the inner radius, inner circle or inner diameter, we can say, of the wheel, and this is the outer diameter or outer part of the wheel. And if you want to draw the vanes which are mounted on this, we can draw the number of radial curve vanes which are mounted on this, like this. So these are the radial curve vanes. So here we can see these are the number of radial curve vanes which are present or mounted on the wheel. And if you see, this is the inner part of this and this is the outer part of this one. So this one is called inner radius or inner circle radius, and this is outer circle radius there. So, and when the jet will be strikes this vane, so obviously it will strike on any single vane, and that is going to strike here in this way, because if we strike in this vertically, it won't work properly because it is a curved one. Okay, anyway, it need to strike horizontally, or you can say horizontal in the sense perpendicular to this vane or inclined to this one. Any one need to be done. So that's why here it is striking this vane at one end of the tip, though it is mounted on a wheel. So what is the force exerted by this jet? We need to find out actually. So previously also we have done similar conditions, but there we have taken only single curve. Okay, and you know that single curve plate or a single curve vane, there is no validity in this. If I take only single part, there is no validity. Like, what will be the practical application in this? Okay, if this is single, this is the plate. If you're striking the jet on this, if you're striking the jet on this single one, where it is practically possible. So there is no possibility in the single vanes. That's why multiple number of vanes are present when it is mounted on a wheel. So that can be considered as a turbine case. Okay, so many applications are there in that area also. So here what I have taken, that this is the wheel and number of vanes are mounted on this, and the wheels are present with a radius of inner radius of R2, and this is the outer radius of R1. So what I mean to say here, both the diameters are different or both the radiuses are different here. So let's consider a series of radial curve vanes are mounted on a wheel, and the radial curve vanes, the radiuses are different. That means R1, which is the outer radius, and R2, which is the inner radius, both are not same. This is, you can see at this point. So though the jet of water is striking this one, so this one we can consider this is the inlet part. Okay, through which the water is coming inside, and after striking this one, the water supposed to be goes out from here. So this is our outlet part, we can say. Okay, and what is the outlet part here? This one. And what is the inlet part here? This is. So what is the distance? Like this is R1 and R2. This is for the inlet condition and this is for the outlet condition. Though the radiuses are not same or both are different, we can say the tangential velocity also different. The tangential velocity of the radial vanes are both are different. Tangential velocity for both the radial vanes are different because both the radiuses are different here. Now let the jet strikes the vane with a velocity of this one v1, suppose, as you can see v1, the velocity of the jet, and once it strikes here, obviously the wheel started rotating. So the wheel, see, once it strikes, it started moving here. Again, the next vane will come. suppose when 2 gone, again when 1 will be there, when 2 will be there, when 3 will be there, when 3, number of vents are present mounted on this. So number of vents are one by one, it is going to strike on that. Now, what about its movement? Now it's initially, actually when it is in flat condition, that time it used to move in the, like, it used to move in the horizontal direction, in this direction. Now here, you see, it is going to move in this angularly, or there is a rotation is there. Okay, so the vanes are going to be rotated here along with the wheel. So what about its velocity? Initially when it is moving in this direction, we used to find out the u1 or u. We used to take u1 or u2 for inlet and outlet condition. But at this condition, how we can calculate, because it is moving with rotationally. As I told you, it's moving with a constant angular speed, we can say. So another part is another terminology. This is angular speed. Okay, omega. So the wheel which is rotating with the angular speed omega, so we can calculate the velocity. We can calculate the vane velocity u1 with respect to omega into r1, and similar, this is for inlet condition, and for outlet condition we can calculate, this is omega r2, this is for u2 at the outlet condition. Okay, these things we need to remember. This is the vane velocity at inlet and outlet conditions. Okay, now, and what are the other terminologies are there? One is r1, r2, as we have seen, and this is new one, angular speed, which we used to denote angular speed is denoted by this omega, and the unit for this is radian per second, and here radius is these are the things are measured in meters. So the vane velocity can be calculated by this. Now we'll go for the triangles, inlet triangle and outlet triangles. See, the triangle part already, actually this is actually called velocity triangle. So this velocity triangle already you've done previously, many times we have seen. Okay, well, these curve plates are there. We have already drawn the velocity triangle at inlet and outlet condition. If you want to see more details, you can see the previous lecture. Just I'll give a hint on this, how I have done. So actually when it is striking, this is the striking part on the vane. So it is striking the vane with an angle of alpha, you can see, because this is the tangential part. Yeah, one more thing also I forgot to tell, that though the radiuses are different, you can see here, the tangential velocity are also different. So what is tangential velocity means? This is the tangential velocity to the vane. So that should be different. Now the next one, the velocity triangle at inlet condition. This is velocity triangle at inlet condition. If you see, now the velocity of the jet makes an angle of alpha to the direction of vane. If I see the direction of vane is this one, so that makes an angle of alpha to this one. So here I can write, if I draw the component of this velocity, because it is makes an angle, some angle is the inclination is there, so we need to consider either vertically or horizontally. So this is the velocity component vertical, and this is the velocity component horizontally. So this one we can write v1, this is cos alpha in this horizontal direction, and vertical direction I can write this is similarly v1 sin alpha. So this indication already I have given. This is the vw1, which is nothing but wheel velocity vw1, and the vertical component is given vf1, that is nothing but flow velocity. Okay, at inlet condition. So these are the terminology. We can see the inlet condition, we can mark it as a 1. At the outlet condition, we can mark it as a 2. So what are the terminology will be there? We can mark it 1, v1, v1, vw1, vf1, and this is vw1 only, the vane velocity, and this is vr1. vr1 is nothing but the relative velocity at the inlet condition, which makes an angle of theta, okay, with respect to the direction of motion of the vane, we can say. So these are the terminologies are there. Similarly, at the outlet condition also, similar conditions will be, similar terminology will be there. Only we need to add it like v2, vw2, vf2. Okay. Now here slightly different. See, our inlet velocity will be always fixed. Inlet velocity triangle will be always fixed. There is no changes in that. But outlet velocity triangle may be different. It depends upon the angle of this beta. Okay. Now see, this is the velocity of jet which is coming out from here, and this is the relative velocity which is coming out from this plate, and which they makes angle of beta and phi respectively with the direction of motion. Okay, and this is the velocity triangle at the outlet conditions. Now we need to find out, actually, before for calculating this force exerted by the jet of water on a series of radial curves, we need to understand what is this triangle, velocity triangle at inlet and outlet conditions. Okay, most previously also I have told you. Just now I have given a few indication about this one. Now I will go directly to the calculation of this force exerted. So before that, we need to calculate the mass of water. First one, we need to identify the mass of water striking per second. The mass of water striking per second for a series of vents. For a series of vents, number of vents we can say, series of vents or plates. Okay, so how to calculate? This is nothing but we can say this is the mass of water which is coming from the nozzle and from per second. This one from the nozzle, in the sense, suppose this is the pipe is there and there is a nozzle is connected to this, and from this nozzle that water which is coming out. So the mass of water. So the mass of water which is coming out from nozzle. So that is per second. So that is nothing but we have seen previously rho A V1. This is rho A V1. So how I have identified? This is nothing but previously also I told you mass per second. This is mass per second, and this one we can write mass equal to, this is density into volume per time. So volume per time is nothing but this is called rho into Q. So rho into Q, this is discharge part I can write rho AV. The same thing I have written here. Okay, this is the mass of water which is striking per second for a series of vents. So this is V1 at the inlet condition. Okay, now here as I told you, this is A equal to, we need to consider area of the jet, area, shortcut I'll write V1 equal to velocity of jet, velocity of jet. Okay, and now you can see this mass of water we have calculated. The next part we need to calculate the momentum of water striking. Okay, the momentum of water striking. The momentum of water striking the vents with tangential direction per second. With striking the vents, you can see striking the vents. Okay, tangential direction, in the tangential direction. So let me write tangential per second at inlet condition, per second at inlet condition. Then we'll go for outlet condition. So what is mean by momentum? Actually, momentum, we know that mass into velocity. We have studied that momentum equal to mass into velocity. So why this momentum is concept is required actually? So now see, when it is striking, the momentum is required because the jet of water, when, see, this is the jet of water, suppose, which exerts a force on the vents. Okay, obviously at what velocity is coming out, and it is giving an impact on the jet, on the vent. Okay, so the force on the vents which is given, so it's changing the water momentum also. See at what velocity it came, and what are the mass was there. So mass into velocity. Okay, so what are the mass was there and what are the velocity there, and after striking, so what is the position or what is the situation of the water? So that changes its momentum. That's why we need to identify what is the momentum of water. So this one we can write, this is mass of water, which is mass per second into the velocity. Now the velocity we need to consider actually tangential direction. As I told you, we need to consider tangential direction. So tangential direction is nothing but the horizontal direction of this velocity. This is the horizontal direction of the velocity. As you can see, this is the tangential direction at this point. So we need to consider the horizontal direction. So that means we need to consider VW1. So we can write this is rho A V1 into VW1. So VW1 is nothing but VW1. So in the bracket I can write VW1 also, I can write component of velocity. As I told you, this is the velocity. Now this velocity, if I resolve in x component, y component, then I can get V1 cos alpha and V1 sin alpha. So this one I can write here, this is V1 cos alpha. Okay. Now similarly, we can calculate the momentum. Again, very simple now. One, we need to understand the first concept, remaining all are simple. The momentum of water striking the vents in the tangential direction per second. Shortcut I'll write per second at outlet condition. At outlet condition. So similarly at the outlet condition also we can write this is mass of water V rho V, sorry, this is 2 rho V 2 we need to write component, and at the outlet condition the component of V2, here if you see the component of V2, the component of V2 in this direction. Now when you consider in this direction actually, so that will be different, so that is VW2 is there, and so what we can write here, that will be in the if you see this one, it is given in the, this velocity is coming out in this direction. Let me draw this one diagram here. See, this is our V2, okay, and this makes an angle of beta here, and this is our VF2, this is our VF2, okay, and this part is the direction of this VW2 we need to understand. So this will be the direction of VW in this direction, but our tangential direction or flow direction we need to we are considering in this direction, but here the wheel velocity, this VW2 is coming in this direction, so the value of this VW2 will be negative. So this is nothing but VW2. So here again we can write this is, yeah, here actually rho V1 is enough, because the V1 actually V1 and V2 both are same we need to consider, okay, and similarly VR1 VR2 also we need to consider the same. Here we can write this is rho V1 into this V2 plate, in the place of V2 VW2 I can write this is minus V2 cos beta, because see this one, if I resolve this one in the horizontal direction, I can write this is V2 cos beta. So what about the direction of this V2 cos beta? That is directing, or that is moving in the reverse direction, so here minus will come. So you can write this is minus of rho AV1 into VW2. Okay, now we have seen the momentum, but here if you see it's rotating with an angular speed, so what we need to calculate, the angular momentum of at inlet condition and outlet condition. So now we need to calculate the angular momentum. It is just simple actually, there is no difficulty. Angular momentum at inlet condition, angular momentum per second at inlet condition. So what is the formula will be this one, already momentum we have calculated, so nothing but as I told you, what is the momentum is there, multiply with radius, okay, so this is nothing but at inlet condition rho a V1 into VW1 into what is the radius is there for this is R1. Similarly the angular momentum per second at outlet condition, we need to write in this way. This is already we have calculated, minus, this is minus is there, rho a V1 into this will be VW2 into R2, radius 2 for the inlet outlet part actually, okay. Now these things completed, mass of water completed, momentum completed, now angular momentum also completed, because this wheel is rotating with an constant angular speed. That's why we've calculated the angular momentum. Now we need to calculate the new terminology, that is called torque, okay, because here force is not required. In terms of torque we need to find out. So here we'll calculate the torque exerted by the jet of water, okay, by the water on the wheel, we can say on the wheel. So why this torque is required, or why this torque concept came here in the sense, so torque is also nothing but we can say the torque is required actually because the force which is applied to the curve ends, the number of curve ends are there, this is, see, these are the number of curved ends are there. So the torque which is required because the force applied to the curve ends, all these things are arranged in a circle. You can see this all are arranged in the circle mode, okay. Now to which is required to rotate and that will be generate a rotating force. Okay, due to this rotation, it creating a rotating force, and that is nothing but torque. Okay, because we have taken a wheel which is a circular part, and number of vanes are attached in this, and it's also rotating in this manner. So that's why the rotational force which is created on this, so that is nothing but torque. Okay, so we need to calculate the torque exerted by the water on the wheel. So here I can write torque equal to, actually this is nothing but the rate of change of, how to calculate this, this is nothing but the rate of change of angular momentum, the rate of change of angular momentum. So what is the formula of this rate of change of angular momentum? This is also very simple. That means initial, what is the initial angular momentum? I'll write in this way, angular momentum, okay, per second. What we have calculated, we can write per second, and minus what is the final angular momentum. What is the final angular momentum per second? What is the meaning of this? This means initial in the sense at the starting, what is the angular momentum at the inlet condition. That means angular momentum per second at inlet condition minus angular momentum per second at outlet condition. So what are the values we got? We just need to subtract this. So what I'll do here, I'll just write the value. This is nothing but rho a v1 into, this is vw1 into r1, minus of minus is there, so I'll make it plus rho a, this is v1 into vw2 into r2. So this is the value we got. Now we can write, this is, we can take a common of rho v1 multiply, this is vw1 into r1 plus, we can write this is vw2 into r2. Okay, so this is the value we got like in this equation. Now this one again we can solve in a short manner, like we can replace the values of this vw1 and r1 in terms of e1 and e2 is there, that we can write. Okay, so this also can be written in this way. Yeah, this one we can write omega r1. Okay, omega part we can write. Now this one cannot be changed, we'll keep it as usual like that. So this is the torque required. Okay, once, like previously what we used to do, once you've calculated the force, there is some displacement, there is some movement is there in the plate, we used to calculate the work done. So here also we'll do the same thing. So though there is a changes or movement in the plate, so here also we'll calculate the work done per second, the work done per second on the wheel, the work done per second on the wheel, So how to calculate this? It is very simple again. Torque, previously what we used to consider, and torque into angular velocity or angular speed, angular velocity actually, that one we can write, this is angular speed I have written. Now this one we can write in other ways. I'll tell you. Previously what we used to do, work done, previously we used to calculate what is the force applied in the x direction into e1, the distance per second. Distance per second is nothing but velocity, so we used to calculate in this way. Here also similar thing, on behalf of force, rotational force, we have taken the torque. Similarly, this is the velocity is there, now we have taken the angular velocity here, omega we can write here. Now we can write the value of this torque. This is nothing but rho a v1 bracket start, this is vw1 r1, and this plus, we can write this is vw2 r2 bracket close into omega, into the omega. Okay, now as I told you that it is moving with that angular speed is there. Okay, similarly this one also we can write, this is 2 into omega, and here omega part we need to enter in this, into this part. That means let make an entry of this angular part, angular velocity in this. That means rho A V1, let it make it inside. That means VW1 R1 into omega, plus similarly VW2 R2 into omega. This is bracket close. Now we can see omega R2 omega R1. So this one we have seen previously, that is called U1. So U1 and U2 can be replaced this. U1 equal to what? This is omega R1, and U2 equal to omega R1 and omega R2. Now we can place this value here and we can find out this is the work done per second, rho A V1 bracket start. This is VW1 into U1, and this is plus VW2 and U2 bracket close. Okay, this is another one equation. Now here if you see this equation, what we got here actually, when the beta value is less than 90 degree. Okay, we have seen this. If you want to see the angle, I will show you. See, this is the angle of beta which is less than 90 degree. Okay, now if you consider the beta, okay, the beta angle, if you consider which is more than 90 degree, okay, which is obtuse angle. This is acute angle and this is obtuse angle we used to call. This is obtuse and this is acute angle and obtuse angle. So in this condition actually we'll get the value of this work done per second when it is more than 90 degree, when the beta is more than 90 degree per second. This can be written like rho A V1 bracket start VW1 U1 minus will get here actually, because see, I'll show you here a diagram. This is the beta part actually, and this is the tangential velocity, or you can say the direction of motion of this fluid, and this is our V2, okay, and this is VF2, and this part is VW2. Now at this condition we got this value. Now when beta will be more than 90 degree, now see, this is beta means this is beta, and the total angle will be 180 minus beta. Okay, now when the diagram will be like this, when the diagram will be, the beta angle will be, now this is our beta angle. Now see, this is our beta angle which is more than the 90 degree. Okay, so in this condition we'll get the value of this minus, in terms of minus we'll get. So we can write this. Now when beta equal to 0 degree, let's suppose when we'll get beta equal to 90 degree, not 0 degree, beta equal to 90 degree. That means this value of this is the beta angle. So how much distance covered here from this point? It is having VW2. So when the beta is 90 degree, like in straight way, it is equal to VF2. So at that position VW2 will be negligible, so that will be vanished. So when beta equal to 90 degree, we can write the work done per second, we can write this is rho A V1 into VW1 U1, because VW part now it is going to be cancelled here. Okay, that is for the previous case I am telling you, like for when the beta is 90 degree. Okay, at this condition our VW2 will be 0. As I told you, this part is going to be 0 because the beta is coming out in this 90 degree. Okay, so general equation if you want to write, we can write the work done per second, if you want to write, we can write in this way, rho A V1 bracket start VW1 U1 plus minus VW2 U2. Okay, this is our general equation. Now in the general equation you can put the value of this 90 degree 0 means this VW2 0 means it will get only this part. Okay, this is our normal equation. Now this is about the work done. Similarly we can calculate the efficiency. So efficiency equal to, we know that the work done per second on the wheel is output. So this is actually, let me denotation is eta, and this is output by input. So here output is nothing but work done per second. This is nothing but the output. And what about the input? Input is nothing but the energy supplied at the inlet condition. So that is nothing but the kinetic energy per second which is supplied to this one. So we can write what is the work done per second we got here. This is nothing but rho a v1, and this is vw1 e1 plus minus vw2 u2. This is our output part. And what about the kinetic energy? This is nothing but half mv square. Half mv square is nothing but half mv v1 square. And this one again we can write, this is also need to consider mass kinetic energy per second. This is per second. So this one actually we can write, this is half rho a v1 into v1 square. Okay. Similarly, we can write, this is rho a v1 bracket start vw1 plus minus vw2 bracket close. Now here we can write 1 by 2, and this is rho a v1 cube. v1 cube. Now rho a cancel, and v1 also 1 v1 cancel, so we'll get square. Now this one, if I want, I can write in this way. 2 part I'll take 2, this term 2 I can take it to the numerator, and 2 into I can write vw1 plus minus vw2 bracket close, and here it is v1 square. This is our efficiency formula. Okay. In the efficiency also again many terminology will be there, like when it will be maximum, when it will be minimum, and what are the conditions will be there. That is in different way. So this is about the efficiency, and this is about the in general form of this is the general form of work done per second. I hope you understand this one. And similarly, the torque part also we have calculated here. Yeah, the torque part, this is the formula for this final one. And what are the steps we have followed? If you want to see, it is very simple. You can see here. Initially, this is our when velocity u1 and u2, that is omega into r1 and omega into r2. And next, first step, we have calculated the mass of water. First one. Second one is momentum. Third one is angular momentum. Fourth one is the torque required. Okay. And the fifth one is the work done. And sixth one is the efficiency. So these are the terminology what we have used, or these are the points we have calculated here. I hope you understand this derivation, though it's slightly lengthy, and I have not explained this velocity diagram in details, because again it will be more lengthy. That diagram you can see in our previous video lecture. And still, if you are having a doubt regarding this, you can give a comment on the comment box. Thank you all.